Good morning. In today's session, we are supposed to see some numericals which will be on the pulse code modulation sampling theorem, signal to noise ratio. All these concepts already we have seen. We have seen the theoretical part. We have seen some numericals also. Again, we will see some numericals because these questions will get asked in the exams. So, what we are saying about the modulations, here we are supposed to do digital transmission of a analog signal. So here we are using the digital communications because digital communication is having lots of advantages over the analog communication, like digital is more viable because it is using regenerative repeaters. It is more robust as compared to the analog, to the noise and the interference. We can code to extremely low error rates, error corrections using the digital communication over analog communications. If you see about the cost, about the efficiency, you can say digital signal are more efficient, they are more cheaper and more easier as compared to the analog. Here we can do reproduction of digital signal very easily without interference, without distortion, and cost is coming down in the digital system faster than the analog system. That's why we are supposed to do digital communication. Then we have seen about the different modulation technique which we are using. So we can see here we are supposed to use modulation technique like a pulse code modulation, in which we can transfer a data, but here we can take number of bits per sample. So here we can say when we are study about the pulse code modulation, we are supposed to do sampling, quantizing and encoding of that analog signal. So here the pulse code modulator, it will samples the input signal at a sampling frequency, and this sampled signal we can digitize by analog to digital converter. So we can see here the block diagram for PCM modulator. But when we are supposed to use PCM modulator, at that time it will supposed to follow sampling theorem. So sampling theorem is nothing but we can say as a Shannon theorem, which will give the statement like a band limited signal of a finite energy which has no frequency component. It will have higher than W hertz. At that time, it will completely describe by specifying the values of signal that can separated by 1 upon 2W seconds, or we can say in the frequency form like a band limited signal of a finite energy which has no frequency component higher than W hertz may be completely recovered from its sample if we are taking its rate, that will be 2 W rates per second. It means what? Here we will require sampling frequency will be greater than or equal to twice of maximum frequency. So you can take Fs equal to 2F max, or we can take Fs that will be greater than equal to 2W. W is nothing but it is the higher frequency content, and Fs will be, here you can take Fs as a sampling frequency. So you can see here in the equation 1, we are talking here about the Nyquist theorem that will tell that you will require the sampling frequency. It means what? In PCM generator, the signal is passed through a sampler which will get sampled at a rate Fs that will be greater than equal to 2 Fm. So here we are saying the output of the sampler which we will get from the sampling process. You can see here in the block diagram of a PCM modulator. We are saying sampled signal as a x of n of t of s. X n t of s. So with its fixed minimum level, it assigns any one of digital level that you can take from x and t of s. You can take any value, and that will result in a minimum error. The error we can call as a quantization error. Thus, the output of quantized signal which we will get from the quantizer, that is nothing but a digital level. You can say that signal quantized as a q of n t of s. So here we will get the quantized signal that we are giving to the binary encoder. So the quantized signal is called as a binary encoder. An encoder will convert that input into a digital signal. You can see the diagram in the figure 2 where we are taking the sample signal and the quantized level. You can see here we are taking the sample signal on the x-axis and we are taking quantized level that will be on the y-axis. So you will get your original signal x of t that will be look like a sinusoidal. So here now we are talking about only encoder side, only PCM transmitter side. Now what we will do here, when we will give that encoded signal which we will get from the quantizer, we are supposed to give to the decoder. It is nothing but receiver side. So we can see the diagram. You can see in the figure 3 which will show us the block diagram of the PCM receiver. We are revising these things because we are supposed to solve some numericals. So here we will see about the PCM receiver which will start by reshaping the received signal, because here we are supposed to remove the error, we are supposed to remove the distortion, and we are supposed to convert our digital which we will get the digitized signal into our original analog signal. So here when we are talking about the receiver side, at that time you can see here receiver will start by reshaping the received pulses. It will remove the noise and it will convert our digital signal into an analog. The received sample are often filtered by low pass filter. The cutoff frequency we are saying as a FC, that will be equal to maximum highest frequency. So you can take FC cutoff frequency. We are not talking about the FS. We are talking not about sampling frequency. We are talking about the cutoff frequency which will be of the receiver. So it will be equal to maximum frequency. So you can take FC equal to FM. So it is impossible to reconstruct original signal because of permanent quantization error which we will get introduced in the quantization at the transmitter side. Because when we have seen about the transmitter side, we have seen there is a, we are doing the quantizer. At that time there will be introduction of two types of error. These are nothing but uniform or a non-uniform quantization error. If the steps we are taking into a same level, at that time we can take that as a uniform quantization. So here we are saying when we are reconstructing original signal, at that time we will get here quantization error, because of quantization error are introduced in the signal, and these error we are saying as a quantization error. Because if you see, we will when we are talking about the transmitter side, you will get here error that will be equal to xq of s, because here we are taking that is the quantized signal, minus our original signal, that is nothing but x and t of s. So you will get here error. So now what we are saying here, so here it is impossible to reconstruct the signal because of this quantization error which we will get introduced at the transmitter side. So the quantization error we can reduce by increasing the quantization level, and this will increase the bits per sample. So here you are supposed to increase the bits which we are denoting by letter V, which will increases the signal rate, and it will require large transmission bandwidth. These equations you will be needed in the to solve numericals. So here we are saying the choice of these parameters for the number of quantization level must be acceptable with the quantization error. So we can see here the reconstruction of signal. Here reconstruction of signal is nothing but when we are talking about the transmitted signal, it is nothing but x of n of ts and t of s, which will be look like a step size, the digital signal. We are supposed to reconstruct signal that will be look like a dotted line x of t. So you can see here the diagram. So here we are saying about the signaling rate in the pulse code modulations, because when we are supposed to reconstruct at that time, there we are saying there is a introduction of the quantization noise. So here we will see about the quantization noise and the signal to noise ratio. We are saying as a signaling rate. So here if we are saying which quantizer will use the number of bits, these are nothing but V, number of binary digits to represent each level. At that time we can take number of level that can be represented by V digits will be equal to Q equal to 2 raised to V. You will get here Q equal to 2 raised to V. So here what we are saying, Q is nothing but Q is the quantization level. So here we are saying we will get quantization level that will be equal to 2 raised to V. V is nothing but here we are taking V as a number of bits, number of binary bits. So the number of bits per second is given by number of bits per second equal to number of bits per sample into number of samples per सेकेंड. तो नंबर ऑफ सैंपल कट हो जाएगा और तुम्हें मिलेगा नंबर ऑफ बिट्स पर second. So you can take that as V into f of s, because sample per second you can take, we are taking sample f of s, we are taking bits V, so you can take V into f of s. So you can take signaling rate, that is nothing but signaling rate you can take as a V into f of s. So the number of bits per second we are calling as a signaling rate, and we can denote signaling rate by letter R. So you can take, you will be required Q equal to 2 raised to V, where Q is quantization error, V is the number of binary bits. You will require equation signaling rate R equal to V into f of s. V is nothing but number of bits per sample, f of s sample per second. So you will get number of bits per second. Now what we are saying here, you will be required f of s that will be greater than equal to f of m. So we can see one example, they you will get the things. If number of binary bits, it means what? Now we are having number of binary bits, it means V equal to 3. Sampling rate, it is 2 sample per second. So what we are saying about the sample is nothing but f of s, sample per second. You can see our PDF here, what we are saying, sample per second. So you can take f of s equal to 2. Find the signaling rate. What is the formula we are having? We are having signaling rate R equal to V into f of s. So you can take V 3, f of s 2. 3 into 2 you will get 6. What is the unit? It will be bit per second. So you can take 6 bit per second. Now you are supposed to find the signaling rate and find the number of quantization level. Number of quantization level means Q. What is the formula? Q equal to 2 raised to V. So you can take Q equal to 2 raised to V. V is having 3. So you can take 2 raised to 3. So you will have 2 raised to 3 is nothing but 2 into 2 4. 4 into 2 8. So you will get 8 level. So number of quantization Q equal to 8 level. Now we are supposed to find about signal to noise ratio and the quantization noise, because there will be numericals on these things also. So you can see here error which will get introduced in the signal at the transmitter side because of the quantization error. We are saying that error as a quantization noise. If you are taking x and t of s, that is the original signal, sample signal, and xq and t of s, that is nothing but the quantized signal. So you will get quantization error epsilon equal to xq and t of s minus x and t of s. So here we are saying x and t of s, it is the continuous amplitude that will be in the range of, you can take x max minus x max to plus x max. So your total amplitude will be x max minus x max. So you will get total, you will get 2 x max. You can take here, you can see here. Now if we are taking amplitude range, that will be get divided into a q levels. So you will get the step size. How you will get? You are supposed to take total amplitude, that will be in numerator. Total amplitude divided by q level of the quantizer. It means what? Number of quantization level. So you will get here, that is you are taking as a, you can take step size, you can denote by letter delta. Delta triangle you are taking. So you are having amplitude range 2x max. So you can take 2x max in numerator divided with respect to the level of quantizer. You are taking level of quantizer as a q, quantization level q. So you can take 2x max upon q. So here if we are saying minimum and maximum values are same, x max equal to 1 minus x max equal to minus 1. So you will get 1 minus minus 1. So you will get 2. So 2 upon q, because when you are talking about the minimum and maximum x max, if signal, that is nothing but our original signal x of t, it is normalized to minimize and maximum value, that will be equal to 1. So you can take x max equal to 1 minus x max equal to minus 1. So you will get value as a 1, because both you are taking 1. So therefore your step size delta, you will become delta, or you can use जो हम differentiation में del नहीं use करते हैं, d and somewhat curve like that you can use, or you can use a triangle for the step size. So you will get, if you are taking both value as 1, you will get delta equal to 2 by q. Now what we are saying here, if delta is small, it can be assumed that quantization error will get uniformly distributed. We are having delta, we are saying it will get uniformly distributed. It means what? Delta by 2 will goes to the positive side, delta by 2 minus to the negative side. So you can take, you can see in the figure 5, uniform distribution of the quantization error, it will show us. So here we are saying quantization noise is uniformly distributed in the equal interval, plus delta by 2 and minus delta by 2. So here now you will get the noise power, because we are saying noise power, power is nothing but you can take v into I, or you can take v into I की जगह v by r. So your equation will become v square by r. So you can take here noise power equal to v noise square upon resistance r. So here we are now talking about the signal to noise ratio. Signal to quantization noise ratio we can define as, it will be the ratio of signal power upon the noise power. Noise power already we have got here. What we are talking? Noise power is nothing but v noise square upon r. Now we are supposed to find signal power. So here we are saying v noise square, that is nothing but the mean square value of a noise voltage. Since noise is defined by random variable epsilon, because we are taking error, you can see we are taking as epsilon. So we are saying that noise we are defined by the random variable. So we can take f epsilon, its mean square value can be taken as integration. Like you can take v noise square equal to integration from, we are taking minus infinite to infinity, but here we are talking about the uniform distribution. So you can take minus delta by 2 to plus delta by 2, epsilon square f epsilon epsilon d epsilon. If we are taking here f epsilon value as 1 by delta, if you solve you will get v noise square equal to delta square by 12. We are talking that as a quantization noise power. These equations you will be needed to solve numericals, because here we are saying about quantization noise power, and for signal to noise ratio you will be required normalized signal power with respect to quantized noise power. But here we are taking quantized noise power, that will be equal to delta square by 12. So now our signal to quantization ratio will become normalized signal power upon we will get normalized noise power, that will be delta square by 12. So you can keep that value as it is. Now we are supposed to solve about the normalized signal power. Sorry, what we are saying here? We are saying if number of quantization value, these are nothing but if we are taking quantization level as Q and number of bit as V, what we are saying? We will get quantization level Q equal to 2 raised to V. Just we have seen here. Like this, the signaling rate 1.1. So what we will do here? We can take Q equal to 2 raised to V. But when we are talking about the step size, if you see our equation 6, what we will get? If we are saying about our step size, we are taking its amplitude range in the numerator and we will dividing with the quantization level. So you will get 2x upon Q. So you are writing here delta equal to 2x upon Q, but Q equal to 2 raised to V. So you can write here 2 raised to V. Now we are having signal to noise ratio, that is nothing but normalized signal power upon normalized noise power. Noise power delta square by 12. Delta we can write 2x max upon 2 raised to V whole square. If you are writing like this, and if you are taking our normalized signal power as P, if you are denoting normalized signal power by letter P, your equation will become, we are solving our equation here like the normalized signal power upon 2x max upon 2 raised to V square, because we are having delta's value, into we are having 1 by 12. If you solve this, you will get the equation signal to noise ratio equal to 3P. This is the signal power, normalized signal power, into 2 raised to 2V upon x max square. These equations you will be needed to solve numerical. So we will solve here one numerical, then you will get the things. Here we are saying a signal that has highest frequency component of 4.2 megahertz and peak to peak value of 4 volt. It is transmitted using the binary pulse code modulation. The number of quantization level is 512 and P equal to 0.04 watt. P is nothing but normalized signal power. Calculate code word length. Code word length means you are supposed to find digital word bit, binary bits. We are taking as a V. You are supposed to find bit rate. Bit rate means R. R equal to signal rate. Bit rate means nothing but signal rate. R equal to, we have seen V into F of S. Now you are supposed to find third, output signal to quantization noise. It is nothing but you are supposed to find here SNR. There will be questions sometime like they will give find SNR. They will give SNRQ, signal to noise quantization error, SQNR. All are having the same meaning. You are supposed to find SNR, which we are having the formula S by N equal to 3P 2 raised to 2V upon x max square. So here now they have given value. What they have given? They have given a signal that has highest frequency component, means maximum frequency. F max equal to 4.2 megahertz. You can take 4.2 megahertz or you can write 4.2 into 10 raised to 6 hertz. And peak to peak value of 4 volts. Peak to peak means what? X max you will get as a 4 volt. It is transmitted using binary pulse code modulation. The number of quantization level Q equal to, they have given 512. Capital P equal to 0.04 watt. Now we will write given these terms. After that we are supposed to find first number, that is nothing but the length of code word. We can take length of code word V equal to, we are supposed to find V. How will you get? We are having the formula. How? Q equal to 2 raised to V. So you can write firstly Q equal to 2 raised to V, which already I have written over before one number. You can see here. I have written here. I have not written the Q equal to 2 raised to V because I have directly taken from the net. So you can see here, you can write step wise. You can write here Q equal to 2 raised to V, but Q is 512, so you can write 512 equal to 2 raised to V. If you are taking log to both sides, your equation will become log 512 equal to V log of 2. So if you solve this, you will get value of V equal to 9 bits. You can solve by calculator also. So here, now we are supposed to find bit rate. Bit rate is nothing but R. R equal to V into F of S. Now we are having the value of V. Just we have solved 9. Fs we don't know. Sampling frequency. But we are having the value of maximum frequency, FM. So you can take sampling frequency equal to 2 FM because we are supposed to follow Nyquist theorem. So we can take Fs equal to 2 FM. So our equation will become V into 2 into FM. V 9, 2 as it is. FM we are having, they have given 4.2 megahertz. So you can take 4.2 into 10 raised to 3. 10 raised to 6 hertz. If you solve, you will get 75.6 megabit per second, or you can say 75.6 into 10 raised to 6 bit per second. Now you are supposed to find signal to noise ratio. How will you get? We are having the formula. Which formula we are having? We are having 3p 2 raised to 2v upon x max square. Now we are having the all value. P we are having, they have given 0.0 watt. You can take directly 0.0 watt. Then you can take 2 raised to 2v. V we are solved. What we will get? 9. So you can take 2 raised to 2v. 2v is nothing but, you can take 2 into 9. You are supposed to write here 18. They have given by mistake 16, but you are supposed to write here 18 because 2v. V we will get 9. 9 into 2, 18. Divided by x max square. X max square we are having maximum peak to peak value, that is 4 volt. So you can take 4 square as a 16. So if you solve this, you will get the value SNR, that will be equal to 33 dB. You can write in the dB or you can take that value as it is. If you are supposed to take in dB, you can use 10 log 10. So you will get the value in the dB. 20 of log 10, 10 of that value. So you will get that value in the dB. So here we have seen about the pulse code modulation. If you see, there are lots of advantages pulse code modulation is having. Like here we can transmit number of bits at a time, and the number of level that will depend on the number of bit. But here if you see, level size is fixed, but it will require highest bandwidth since we are transferring here number of bits per sample. So here we can say advantages of PCM, like its effect of noise is reduced. PCM will permit the use of pulse regeneration, and it will do multiplexing of various signals. So these are the some advantages of PCM. If you are talking about the disadvantages, its system is complex because here we are supposed to transmit number of bit per sample, and there will be no feedback in the transmitter and the receiver signal. Again, if you see, there will be the highest bandwidth will be required since number of bits are high. That's why there will be the need of another improved version of the modulations. So there is a need of another modulation technique. So we will see about delta modulations, differential pulse code modulations, which will uses the bits that can be more than or the less than pulse code modulations. But here number of level will get fixed. And if you compare with the pulse code modulations, here it will require less bandwidth. It means what? Differential pulse code modulations will be improved version of pulse code modulations, which will reduces the requirement of bandwidth. It will reduces the value of bandwidth. And here if you see, there will existence of a feedback also. And if you see about the circuit diagram, here it will get simple circuit as compared to the pulse code modulations. Then we will see about delta modulations, adaptive delta modulations. Here we have finished numericals on the pulse code modulations. Thank you.